requirements. And for the first requirement, the rover must be untethered. The arm board may be mounted on the rover or stationary and talk to the rover wirelessly. Must have a web page interface for our rover, and where the web interface is hosted on the arm. And we must designate a point on the rover for measurement of rover location. And finally, rover must be I2C communicating, and that's between multiple components. For the first one, we got to go in a straight line, which we send our command to the rover. It does what we want to do, which is a straight line. Second, we want to go to an XY location, like an XY coordinate, which means the rover can be right here, and we want it right here. So the rover has to figure out how to be going in that direction. And this is with no obstacles. No obstacles. Right here, go to the XY location with obstacles. So now you have the rover here, you want to get to this point here, so there's just stuff all over the place, whatever. So the rover has to find out how to get to here. So it's going to do all sorts of things and get to here, of course using the shortest route. Seek an object, which is our cube, which we created, we show that you later, with no obstacles in less than 10 minutes. So that means if the cube's here, the rover's here, it has to navigate around using the algorithm and finally get to the cube. That's with no obstacles. Of course, it's going to be the exact same with number 5, with, let's say, there's obstacles in the way. And then the rover has to figure a way to get to the cube once again. Okay, and this task 4 and 5 must report the cube's location on an arm board, which we discussed later. And a cube can be 6 inches.
As you can see, it's made out of cardboard. It's pretty basic looking. It's got IR LEDs all around the outside. There's 24 of them in total, 6 per side.
So awesome.
On the top, there's an on-off switch that basically just turns it on and off. And on the inside, as you can see, it's wired up. There's some resistors in there and our battery. Our battery is a 12-volt battery, and it runs through a large current limiting resistor that prevents LED burnout. And the LEDs communicate with the the IR sensor on the rover. These LEDs are mounted at the same height on the cube as the IR resistors are on the rover, so that they can be seen most efficiently. As you can see, there's one right here on the front, and then there's one on the right side, and one just like it on the left side.
Nice.
They run up and through this op amp right here, and through these resistors so that they can be amplified as the current and power that run through the resistors themselves is very low. They then from there run into the 3 of the ADC ports on this PIC right here. There are these 3 wires right here. And for reading these, we had to change the timing on the ADC read from ADC 0 TAD to ADC 4 TAD, just so that we could allow it to read each sensor individually without any overlap or any error. When these sensors do see any kind of IR emitting, they do cause an automatic stop of any wheel movement, so that we can stop and send data up to the arm and say that we've found the cube and that we simply need to turn in that direction and navigate to it from there. As you can see, the sonar sensor is mounted at the bottom on the front of the rover. We did this to help make sure that it would see anything that would possibly be in its way. We worried that if we put it too high, it might not see things that were low, and that it would still run into them, and that would get in the way. The sonar sensor constantly pulls distance. It runs off a timer interrupt, and then it does the read ADC, and it reads and pulls in the data. The data comes in centimeters, and because we needed it in inches, we had to multiply it by 0.39 to get it then into inches. We found that occasionally the sonar sensor needed to be recalibrated based on the power it was getting. If the power was higher or lower than normal, we had to do a polling.
So for navigation, basically once I get the map from the mapping task, it utilizes an algorithm called wavefront. And the way the wavefront works is it basically finds the shortest distance from the start position, which is the rover, to the end position, which could be whether how many feet that we needed to go, or it could be where the obstacle or where the goal was, the cube. So for example, this is our starting position for the rover, and the way that we utilize it within code is that we use the value 1 as obstacles. So if I were to place obstacles here and here, and if I were to set the goal position to here, then the wavefront would actually run, and it starts off at the goal position. So it searches the map until it finds the goal. Once it finds the goal, it places numbers adjacent to the goal. So for example, we're going to start off, since we use 1 as the obstacles, we're going to start off utilizing the number 3. So the way that this works is it will search through, find the goal. Once it finds the goal, it will place a 3 in every single adjacent block. And then it will continue on. So 3 is here, 4, 4. So we can either go this way, 8. So in this case, it doesn't really matter which way we go. It's just the longest path would actually be if we go this way. So we can either take this path, go all the way down and reach the goal, or we can take this path, go all the way down and reach the goal, which turns out to be the same distance. We utilize the normal convention for north, south, east, and west. So north, south, east, and west. And we utilize this to basically set the direction in which the rover is facing. So this is important so we can make sure that we make the right left and we make sure we make the right turn. If the rover is facing north, then we know we need to go east or west. Within the code, it would actually have an algorithm to determine this. So it will go step by step, and it will continuously update the direction in which the rover is facing. And that's basically navigation once it reaches it. All right, for this task, the algorithm first starts off as random for navigation. So within the code, I still utilize the wavefront. So for example, if the rover position starts off here, I will arbitrarily place an end position. The wavefront will run, and once it reaches this end position, and the cube still has not been found, then it will arbitrarily pick another position. So once the rover gets down here, I will reset the goal position to here. For example, if the cube was placed, the way our design works, once the rover reaches here, an interrupt will be triggered, which basically says that the cube has been found. Once the cube is found, the rover will stop, the goal position will be placed where the cube is, wavefront will run again, and then we'll find the shortest distance to the cube.
First being the Sabertooth 2X12, which is the motor regulated 5 volts out with 1 amp. Now we're using this to power pretty much everything that's on board. 4 DC motors, which drives the rover. But we decided to use serial communication, which the PIC has hardware able to detect the rover's movement. Since there's 2 sensors that are 90 degrees out of phase, you can actually detect direction of the motors. The bump sensor. That's just a failsafe, just in case our algorithm did not pick up, or our sensors did not pick up an object in front of the rover. We could, using a tactile switch, hit an object, and this is our impact bar. You can hear it. And you know, if it rover's rolling along, you know, going over things, all of a sudden it's like, oh, we didn't see the series. With these, it needs about 2.8 volts to 3.6 volts. No more than 3.3 is what the data sheet requires. Also, indoor it has about a 100-foot range, which was unnecessary in a 20 by 20 room, and outdoors is about 300 feet. If you look at the rover here, you can see our placement. Now, how do I step down from 5 volts, 1 amp to about 3 volts? Well, I have a voltage regulator here. It's a variable voltage regulator. Have it set up to about 3.3 volts, which makes the XB happy. The PIC is communicating this transmission line right here serially, and then you have a receive right here also transmits through the wire, the XB wirelessly. Also, it's interrupt driven. These are the interrupts. When you hit the bump sensor, it goes back. See the
when the mapping first starts, it sets the initial rover position and goal position, and also it also takes into account the rover direction. So right here on the map, we would have the rover position set at the middle, and it's facing north. Then the next thing that happens is that the sonar data comes in and gives a distance of anything that is in front of the rover. So let's say that there's an obstacle 3 feet in front of the rover, then it will use a rotation matrix equation that will determine, taking into account the heading, and then plot it onto the map. So it will, depending on the rover position, it'll rotate it to the right heading, so north, and then translate it onto the map. The obstacles are also padded. This is just for in case the rover gets too close to the actual obstacle. If a bump sensor is triggered on the rover, then an obstacle will be placed where the rover was. That is included is cube detection. Whenever the rover detects a cube using its IR sensor, which IR sensor it detects it from, the rover will turn in that direction facing the cube and then set that marking on the map. With the sonar sensor, it'll find its distance, and then the navigation task will basically navigate around.
Speed, reliability to wireless communication. There's been numerous times where the arm would send out communication or commands to the rover via the XB, and on the master PIC XB as well. There's been, I guess, packet loss, memory management on the ARM code. Since the mapping requires a substantial amount of data, there's been times where it'll just get to the point where it's be tight. Our sensor depends on the lighting. We will have to recalibrate the sensor every time. That became an issue because, as you can see, lighting's pretty good in here. In the cell, the lighting was adequate, and we weren't having any issues in the beginning. Will be the sonar sensor. There's been times where we just give false readings. As in, let's say you're 20 feet from something, it will say that you're and of course, during running the algorithm, if you run into false readings like that, your rover will react accordingly and give you inaccurate results. And also for every room, like I said, this room is different from our lab, different from the cell. The way that we have the rover moving, the turns aren't always accurate 90 degrees, what we need. We don't always get that. As well as distance, roller resistance, all sorts of things could play, dust, all that will throw off all your readings and all your readings in the sense of wheel encoder data. And we decided, with the improvements, we could have it somehow self-calibrate, maybe something. For the sonar, also self-calibrated, though it has a feature we have to go in there manually to calibrate that. For the RR, we have figured out a way to calibrate that as well, but again, it should be something that should be self-calibrating. And for memory management issues, we just had to reconfigure the code. And then for reliability wireless, we don't know if we're getting other kind of interference. Since there was a lot of groups around, that could be something very small. But in our single testing, we were getting some loss, but there needed to be some sort of improvement there too.
The first is with wireless communication. We were using the XBs. The Series 1 would give it a 100-foot range indoors. And from our picture here, you can see how the XBs are attached to this PIC through UART. And on the rover side, the XB is attached to the PIC master through UART as well.
Okay, and this is our web server. It's a basic layout. It has functions for the different tasks. Basically, you input a value, whether you want to just go straight, you input how long you want to go straight. If you want to, do a turn with an obstacle, you input that as well, and also the task that involves an obstacle. These functions are basically programmed within the ARM code, the UIP task, and it is passed through a queue to the actual mapping task so that these values could be used and the code for the function to be sent over to the rover.
We have the freaking entire.
You see how it's turning a little bit? It's not straight.